So, good morning to all of you present here in this class. I hope I am audible there and you can see the screen as well. Am I audible there and screen is visible to you, the PowerPoint
Yes,
presentation?
sir.
All right, so let us begin with the next part of the lecture which we were discussing yesterday. So yesterday we were discussing about this reciprocal lattice and we had seen the Fourier series. And how Fourier series acts as a connecting bridge between real space lattice and reciprocal space lattice. They are also known as one, if one is called, say, the real space, other is called Fourier space. That's another way of looking at this. Before I proceed further, I would like to ask you if you have any confusions or questions from what we have done yesterday. Please feel free to ask any questions from what we have done yesterday. Anyone has any question? Don't understand the difference between both lattices. Okay, Shreya. Fine. Anyone else? Very good. Others, please. I will try to talk on what is the confusion of Shreya. Then next, any other question? Okay, the significance of first expression in this slide. Fine, that I will be showing, or we will be talking about that. What else? Any other query? Any other question, please? Well, if there is no other question, uh, before we proceed further, let me again demonstrate this concept of real space lattice and reciprocal lattice with the help of these simple examples, which I am trying to show up here. Yesterday, we were trying to visualize things in our own imagination. So today I have tried to bring in the specific example on the slide itself. So let us assume we have a one-dimensional lattice, which is nothing but periodic arrangement of points. So here these red dots are actually representing a one-dimensional lattice. And we have enlarged the points to look them like dots, bigger dots on the screen. Otherwise, if they are just dots, we can't see them with the naked eyes. I hope you know all this. So if this is a lattice, what will be the translational symmetry associated with this lattice? T is equal to n1 into a, where n1 can be some integer, where if a is the separation between any two lattice points, how will the lattice points be repeating? If suppose this point is taken as a reference, then you will have a lattice point at a separation a, 2a, 3a, 4a, and so on. And similarly to the minus side, minus a, minus 2a, minus 3a, and so on. So what are the values of n1? Sorry, it's not n, but it is n1 because we are using n1 notation here, so that it can be generalized later for 2D and 3D case. So what will be the values of n? So n1 is equal to 0 for this case. It is 1 for this lattice point. It is 2 for this lattice point, and so on. So that all these translations are basically representing the symmetry operation of this lattice. Means the lattice is invariant with respect to these translations. If I go from this point to say this point, I won't be able to see any specific difference. So the whole lattice will look exactly same. Either I am at this point at 0, 0, 0, or 0 for 1D case, or I am at A, or I am at 2A, or I am at 3A, and this lattice actually extends to infinity. So there is practically no difference. Well, so what will be the corresponding reciprocal lattice for this? You know, the Fourier series, which we already have done. So it will have corresponding, it will also be a linear lattice. To view, it may look exactly the same way, but it's not exactly the same way. The lattice vector, so in this case, in real lattice, the lattice vector is A. So in reciprocal lattice, the lattice vector will be 2 pi by A, right? And what will be the corresponding translation vector? So in real space, we write this translation vector with the T. In reciprocal space, we write the same vector with the notation G, just to differentiate them from each other. So what will be the generating vector for a reciprocal lattice? We can say this is something like V1 times A star, where V1 is also some set of integers. As we have N1 for real space lattice, we can take a different notation for the integer generating the reciprocal lattice. So how will be the points in reciprocal lattice looking like? So if one point is at say 0, the reference, there will be another point at A star, 2A star, 3A star. So this is the reciprocal lattice vector. So that is how we can establish the relationship between real and reciprocal space lattice. And what is this reciprocal? This is what is this G representing? This is representing the translation operations with respect to what? Our reciprocal space lattice is invariant. So T represents the translation operations with respect to which the real space lattice is invariant, and G represents the translation operations with respect to which the reciprocal lattice is invariant. I hope this is clear to you. So that if we have any periodic, say, quantity, in case of crystals, we may have electron density, which is periodic. So this can be written with the help of Fourier series, and the Fourier series relates these two, right? So this is from where this 2 pi by A terms coming into picture, and how the two are related to each other. So this reciprocal lattice try to mimic the periodicity of real space lattice. So that is what is the relation between the two. Fine. Still okay. Where is the question? Shreya. Shreya, I mean, even till now, you couldn't understand the difference between the two lattices, or is it somewhat improved now? Shreya, you still have a confusion, or it is clear? Shreya, expecting your answer. Yes, sir is not the answer. I mean, yes, sir means you have a confusion or it is not clear. Significance. Okay, we will be coming to the significance. That is okay. Let us first understand what the two things are. Then we will move to the significance. Don't worry. What does the point in reciprocal space correspond to in real space? There is nothing like one-to-one correspondence between the points in reciprocal space and the points in real space. But yes, the points in reciprocal space tells you about the terms which should be there in the Fourier series, right? So for example, if you have to represent a function which is periodic with periodicity, say A, then the corresponding Fourier series will contain terms which will be having frequencies at say 2 pi by A, 4 pi by A, 6 pi by A, and so on. Or I can say A star, 2A star, 3A. So the reciprocal lattice just tells us about these terms. Okay, at what frequencies the terms should appear in the Fourier series. The terms of which frequency should appear there. So there is nothing like, okay, this 0 corresponds to this 0, or this one, this A corresponds to A star. No, not like this. There's nothing like one-to-one correspondence. Is that clear, Harish? Fine. So very good. Significance of this will be coming shortly. And then there is a Is there any other question? Okay, significance of, Dipali was asking significance of first term in the slide. So I'll be coming to that slide, so no problem about that. Okay, so that is what is the relation between real space and reciprocal space lattice. And now let us try to understand the same example for 2D case. Suppose we have a two-dimensional lattice. In this case, we have taken a simpler example because in 2D there can be 5 different Brilloiun lattices. So in this case, we have taken the simple one only. It may be looking like rectangular, where A and B are the say. Suppose we have chosen A and B to be the primitive lattice vectors. So A is the vector connecting this and this point. B is the vector connecting this point. So when we repeat the lattice points according to these vectors, we will be able to generate the whole lattice in the 2 dimensions. So what will be the translational symmetry, or what will be the translational operations with respect to which this lattice is invariant? So this is going to be the translation operations in 2D case. So n1 into A plus n2 into B, where n1 and n2 are some integers. So if I take n1, n2 to be 0, I will be at this point. If I take n1 equals 1, n2 equals 0, I will be at this point. So whether I am at this point or at this point, the things are totally undifferentiable. If I take n1 equal to 2, n2 is equal to 0, so I am here. If I take n1 is equal to 0, n2 is equal to 1, so I am at this point. If we take n1 and n2 both 1, so we are at this point, and so on. Means by taking this translational vector, we can generate the whole two-dimensional lattice. And that's the one way of looking at it. And other way of looking at it is that if you take any if you sit at any point in this periodic structure, not only on the lattice point, and do a translation by this amount, you will be going to some other point which will be exactly the same. For example, suppose I'm here in the midpoint of this cell. Then if I do a translation along A by value, say n1 is 1 into A, so I will be coming to this neighboring cell. So this point and this point are going to be exactly the same way. Means any operation in this 2D lattice is translationally invariant with respect to this translation operation. I hope it is clear, right? So what will be the corresponding reciprocal lattice for this? I hope you have somewhere gone through two-dimensional Fourier series. If not, you can go back to some of your books, maybe somewhere you will get that. So basically what we are trying to do here also is that we are going to use two-dimensional Fourier series. And again, what is the thing here is that what all terms are going to appear in the 2D Fourier series, they are defined with the help of these reciprocal lattice vectors. So A star is given by 2 pi by A and B star is given by 2 pi by B. And what will be the corresponding translation operations in reciprocal lattice? They will be given by this G vector now. So how would the 2D reciprocal lattice look like? To visualize on screen, it may be looking to you that I have just done a copy and paste. Yes, I have practically done that, but technically they are little different. So basically now B star will be longer one and A star will be smaller one. So these two will interchange. Why so? I mean, along the direction B. So in this case, this vertical direction is B direction. So in this case, I have taken horizontal direction as the B direction. Why? Because B star is inversely proportional to B. So the longer axis in real space will be shorter axis in the reciprocal space, and this one, say A and A star, and the shorter axis in the real space will be longer axis in the reciprocal space. And that is what is the important point to note here, that okay, this is how we can generate from a real space lattice to a corresponding reciprocal space lattice. So you have to get corresponding vectors. So first thing you have to do is, okay, you know that it is already given to you that this is the real space lattice. Now how to get reciprocal lattice? From that, you have to first find the reciprocal lattice vectors from the real space lattice vectors. So this is the relation. So you first have to look for the relation between real space primitive lattice vectors and reciprocal space primitive lattice vectors. Then you have to look for the generating rules. I mean, what will be the rule according to which we can generate the reciprocal lattice? So we will be in a position to generate the reciprocal lattice. So these, once you have the reciprocal lattice with you, you will be in a position to write down corresponding Fourier series for a particular two-dimensional periodic structure or even three-dimensional periodic structure. Um, well, before I move to the 3D case, I would like to ask you if there is any question from anyone. Yes, any question? Is this clear to everyone?
Yes, sir.
Okay, Anshul says okay, Ankush says okay, Dipali says okay. What about others? I see only 2-3 people responding. Well, so many responses. Very good. Means okay, it is clear. I assume it is clear to everyone. Now let us move to the 3D case. So basically, in 3D case, if A1, A2, A3 are the real space lattice vectors generating the real space lattice. So first thing as we should do is to find out the corresponding reciprocal space lattice vectors. So now notation is changed a little bit. Now I am using A1, A2, A3 for the real space lattice vectors and B1, B2, B3 for reciprocal space lattice vectors. So if you have been given the real space lattice vectors by A1, A2, A3, these are vector quantities, then the corresponding reciprocal space lattice vectors or primitive lattice vectors are given by this B1 is equal to 2 pi A2 cross A3 divided by A1 dot A2 cross A3 and so on. So the exact derivation of this comes from three-dimensional Fourier series, which is in itself a very long time-consuming exercise. We don't need to get into that because as such it may be required for a mathematics student, but we will be using it directly here. So this is, I mean, technical relevance or the physical meaning of the same should be clear to you. That what is this reciprocal lattice vectors telling you? Now, what are these vectors telling you? They are going to tell you the lattice points in reciprocal space which will be constituting the corresponding Fourier series in the three dimensions, right? So what is the generating rule then? G vector. So this is now for 3D case. This is V1, B1 plus V2, B2 plus V3, B3, correct? So this is the translation vector for the reciprocal lattice. Means again this will be the vector which will be the giving us the relation for translational invariance of the reciprocal lattice. Now Dipali was asking, okay, what is the significance of the first term here appearing here? So basically, this first term just tells us the relation between the real space lattice vectors and reciprocal space lattice vectors. So this can be derived from these simple cases. I mean, suppose I take B1. So this is Bi dot Aj is equal to 2 pi del Ij. So let me take I is equal to 1, J is equal to 1, right? So this will be like B1 dot A1. This is just a dot product of two vectors. And what is B1 vector? Let us put it as 2 pi A2 cross A3 divided by A1 dot A2 cross A3 dot, this is B1, right? Dot A1. So when you take the dot product, so this numerator will be what? A2 cross A3 dot A1. And you are familiar with the properties of scalar triple product. So A1 dot A2 cross A3, I mean, the cyclic order can be changed. So this will be exactly same as the denominator. So these will cancel, and what is B1 dot A1 giving you? 2 pi into I is equal to J here, 2 pi simply, correct? Numerator will cancel with the denominator. But if you take I'm sorry, I is equal to 1, J is equal to 2, so then I have to take B1 cross B1 dot A2. So when I take the dot product, then this numerator will go to 0, because if any two terms in scalar triple product are same, the scalar triple product is equal to 0. So that is going to give you 0. So this just tells you the mathematical relation between real space lattice and reciprocal space lattice. I mean, how the two are directly related. And that's all I can see right now for this expression. Still, is it clear or not? I mean, is there any further question for this? Oh, my voice is breaking. Chetna says, I don't know. Is it anyway better now? Is my voice audible or okay now? Okay, I hope you didn't miss it for longer. So could you get the idea of the relation between A, I, and BJ? Was it clear, or I need to repeat this? The relation between AI and BJ. Okay, I need to repeat this. Okay. I will repeat, fine, no problem. Okay, I mean, see, this is just telling you the dot product of B, the reciprocal lattice vectors with the real space lattice vectors. So these are all three reciprocal lattice vectors for, I mean, in the reciprocal space. Now, if I take the dot product of any of the reciprocal lattice vector with any of the real space lattice vector, so what will be the outcome? This relation tells you about that. So here is bi dot aj. So I can be 1 to 3, j can also be 1 to 3, independent of each other. So if both I and j are equal, let us take b2 dot a2. So if I take dot product of b2, so I have to write down b2, then dot a2, and then if you take dot product, then numerator here will be a3 cross a1 dot a2. So this is going to be exactly the same as in the denominator, because cyclic order, if it is kept fixed, then the position of the vectors can be interchanged in the scalar triple product. And what will this give us? The numerator will cancel with the denominator, so this will be 1. So what will be b2 dot a2? That will be equal to 1 into 2 pi, right? So that is what is this relation telling us. Similarly, you take any, I mean, I equal to 1, j equal to 1, same thing you will get. Similarly, I equal to 3, j equal to 3, same thing you will get. But if you do other way, I mean, if we take I equal to 1, j is equal to 2, in that case, we will be multiplying with b1 with a2. So if I take b1, this is b1, multiply it with a2. So what will be numerator? a2 cross a3 dot a2. So that will be 0, because in scalar triple product, if any two vectors are equal, the scalar triple product is equal to 0. So that will be 0. So this is what this relation is depicting. So whenever I is not j, this is 0. Whenever I is equal to j, this is 1. And this is what this relation tells us, that how are real and reciprocal lattice vectors related to each other, or we can say they are orthogonal to each other, isn't it? Orthogonal may not be a good term. I don't know. I mean, I equal to j. I mean, that is how you can say this. I mean, if I is j, that will be equal to 1. If I not j, that is not equal to 1. That is 0. That is what is the relevance of this. So as of now, I can see only that is the relevance of this expression. If something will be coming later on to my mind, I will share it. But still, if there is any question you have in your mind, then maybe I can try to find out answer to that. From where does the expression for B1, B2, 3? So this comes from a 3D Fourier series. I told it earlier, so we don't need to go to the details of the 3D Fourier series. Just like you did it for 1D case, it will be given for the 3D case. You can, if you are interested, you can go to some book on mathematics where where they have described 3D Fourier series in detail. So there you can get the idea. Just same way it is done for 1D case. In 1D case we have this expression, right? In 1D case we have this expression. So similarly, for 2D case there will be corresponding 2D Fourier series. For 3D case, there will be corresponding 3D Fourier series. So there, in 3D Fourier series, you will have three components: 2 pi p x by a, then 2 pi, say maybe instead of p we can write down p1 p2 p3, or v1 v2 v3 as we are using. Then 2 pi v2 y by b, 2 pi v3 z by c maybe, or A3, A1, A2, A3 actually. So that is how they are going to look. But that is not going to be as simple as this one. There will be little lengthy terms there. So I refer you to go to that. So we are here using it directly because we don't have that much time to cover all the details, mathematical details here. So we have to complete things well in time. And of course, for a condensed matter physicist, we don't need to get into too much of mathematics. We can directly hire that expression from mathematics and then go ahead with what we actually have to do. Otherwise, we will be lost into what we are not supposed to do. Okay, fine. So, but the physical meaning should be clear. So, what are these vectors telling you? These are telling you that what will be the reciprocal lattice corresponding to any given lattice. And what is this telling you? This is telling you where all the terms will be coming in the Fourier series. So this is telling you that every point in the reciprocal lattice will tell you one single term appearing in 3D Fourier series, right? As in the case of 1D. So that is what is the relevance. Okay, there is another question. Does it corresponds to the allowed lattice vectors in Dipali, I didn't get your question properly. Can you please properly elaborate it what you mean to say this? Allowed lattice vectors in reciprocal space. Please repeat your cross question properly. I couldn't understand this one. Dipali, please try to redefine or little elaborate your question so that I can help you. Okay, what is your question is, okay, the lattice vectors in which I equal to j. What do you mean is, okay, does it correspond to the allowed lattice vectors in 3D? The lattice vector in which I is equal to j means they are along same direction. Because if you see, okay, if you go here to these expression, so, well, I mean, if you see B1, B1 is going to be a reciprocal lattice vector which is perpendicular to A2 vector cross A and A3 vector both. So, if you have mutually perpendicular vectors, like you have a simple cubic case or any cubic system, then the lattice vectors are, if the lattice vectors are perpendicular, primitive lattice vectors are perpendicular to each other. In that case, third vector B1 is actually going to be exactly parallel to A1. But in case there may be a situation when A2 and okay, I mean A2 and A3, so B1 will always be perpendicular to A2 and A3. Similarly, B2 will be perpendicular to A3 and A1. So this is not necessary that B1 is parallel to A1, but yes, in case of cubic situation, B1 and A1 will exactly be parallel, right? I have to do some mental exercise to visualize what will be the case for non-cubic cases where the primitive vectors are not um perpendicular to each other. But okay, you can do that yourself as well. But yes, I is equal to j represents the same, the only case. I mean, a vector probably parallel to a vector in reciprocal space which is parallel to the vector in real space. That's maybe the way to say. I mean, uh, allowed lattice vectors. I don't understand what you mean by saying it as allowed lattice vectors in 3D reciprocal lattice. All are allowed. I mean, A, B, C. Sorry, I is equal to 1, 2, 3. All are allowed. I mean, B1, B2, B3. I equal to j is nothing like it is a allowed state. No, I don't think that is the case. If I am correctly understanding your question, is that somehow helpful, or you have any further doubt? Okay, anyway, fine. Then let us move to the next. Well, so now that is from where the idea of a Brilliant zones comes into picture. In our previous slide, we had seen this, that how to get Brilliant zone for a 1D case, right? So basically, Brilliant zone is nothing but Wigner seed cell in uh, any particular lattice. So Wigner seeds for 1D case, Wigner seed cell is quite simple. You take any lattice point as a reference, connect it to the neighboring points, draw perpendicular bisectors, and this innermost cell is called the Wigner seed cell and also called the first Brilliant zone. So 1D case, it is quite simple. Then let us discuss. Okay, before I do Brilliant zone for 3D case, because they are a little complicated, let me show you the Brilliant zone, how to draw Brilliant zones for two-dimensional case, and how to understand the meaning of the Brilliant zones technically. So for that, I would require to share my another screen, because there is a very nice demonstration on a website available online. So just a minute, give me some time to get that done. Okay. Stop presenting. Present now. Window. I don't know if this will be coming to you or not. Let us try. No. Okay. Let me share the whole screen then. Entire screen. Okay. I hope now you are able to see my full screen, and now you are able to view this website, which is showing a 2D square lattice. Is this tab available, visible to you? This 2D square lattice. Now you must be seeing the screen of Google Meet, but now when I will switch to that tab, okay, fine. Now I'll be showing you how to construct a Brilliant zone in two-dimensional lattice. So 1D is clear to you. I hope all of you. That is very simple. Now let us come to 2D case. So we have seen that, okay, there is a real space lattice. Then from that real space lattice, we now are in a position to obtain any reciprocal lattice. So if our real space lattice is a square lattice, 2D lattice, then the corresponding reciprocal space lattice is also going to be a two-dimensional square lattice. But the separation between lattice points will be different. I mean, in real space, the separation between two lattice points are suppose A. Then in reciprocal space, the separation between two lattice points will be 2 pi by A. So this is now suppose two-dimensional square reciprocal lattice. Now let us see how to draw Brilliant zones in 2D lattice. So what is our procedure? Is actually to draw 2D Wigner seed cell, right? So we choose one point as a reference. So let us assume I am taking this point as a reference. Then what we have to do, we have to connect this point to the neighboring lattice points. So I draw one connecting vector, then draw a perpendicular bisector, correct? Then we have to do it for all others as well. So for this one, this will be the perpendicular bisector. For this connection, this will be the perpendicular bisector, and so on, correct? So in this way, this innermost cell which we obtain is called the first Brilliant zone. This is called the first Brilliant zone. Is this clear? This is quite simple, but still, is this clear? Any question? Well, fine. Now let us try to draw other Brilliant zone, higher Brilliant zones. So for that, what we will do, we will again connect this point to the neighbors which are little further away and draw the corresponding perpendicular bisector. So for this set, This is the perpendicular bisector, correct? Now we do it for all other neighboring points. So for this set, we will be getting this as a perpendicular bisector. This as a there will be 4 perpendicular bisectors. One more thing, that these perpendicular bisectors are also called Bragg's plane. These perpendicular bisectors are also known as Bragg's plane. Why so? We will be getting this in the next lecture. So these are called Bragg's plane. So this is your first Brilloiun zone. What will be the second Brilloiun zone? It will be the area, the whole area in the reciprocal space, to which we have to go from first Brilloiun zone by crossing only single Bragg's plane. Means the whole area in the reciprocal space, which we can access after going out from the first Brilloiun zone by only crossing one single Bragg's plane. Fine. So now this is your first Brilloiun zone. This is a Bragg's plane. This is a Bragg's plane. This is a Bragg's plane. This is a Bragg's planes. Correct. Now, what all area is accessible after going from first Brilloiun zone, for which we have to cross the single Bragg's plane only? So this full triangle, this full triangle, this full triangle here, this full triangle, all these 4 triangles actually constitute our second Brilloiun zone. Oh, sorry. Yes, because if you go from here, if you say, okay, why not this one? So if I have to go to from first Brilloiun zone to this area, I have to cross the Bragg's plane 2 times, one time here, second time here. So this is not the area of the second Brilloiun zone. So this whole area is called the second Brilloiun zone. Is this clear? Is this clear, or any confusion? Yes, waiting for your response. Clear to Harish. What about others? Bhai Himanshu, this is in reciprocal space. Right in the beginning, I said this is reciprocal space. In reciprocal space, we call Brilloiun zones. In real space, we call the unit cells. You may say it that way. Okay, fine. Now let us try to see how we can get the third Brilloiun zone. So what we do, we try to connect our reference point to further away lattice points, then draw perpendicular bisectors, repeat it for all others. So this will be the new set, and this area. Now what is the definition for third Brilloiun zone? It is the area in the reciprocal space which we can access from second Brilloiun zone after only crossing the single Bragg's plane. Again, now suppose you are in second Brilloiun zone, that yellow area. Now what all area is accessible only just after crossing a single Bragg's plane? So this area, this area, this area, this area. So all this area is accessible after just crossing a single Bragg's plane. So this area of the reciprocal space is defining third Brilloiun zone. Fine. Let me directly go to the fourth case, fourth Brilloiun zone. Again, let us draw some other next neighbors. Draw perpendicular bisectors. Do it for all. So that you to do this systematically, you have to put some efforts on maybe a graph paper that will be giving you a better understanding. Now again, what will be the fourth Brilloiun zone? All the area of the reciprocal space which is accessible from third Brilloiun zone by only crossing a single Bragg's plane. So if this is the third Brilloiun zone, so this whole area is accessible after crossing, and from here this whole area, but not only this area, but this is your third Brilloiun zone. This small portion also is accessible after crossing the single Bragg's plane. This area is also accessible. So that is what gives you the fourth Brilloiun zone. Okay. Similarly, you may try to get the fifth Brilloiun zone. Then maybe sixth Brilliant zone if it is there anyway. Now you may ask, okay, why didn't you join further neighbors and draw further perpendiculars? You could have tried, but then those Bragg's planes may be lying way outside these already drawn. So maybe we don't need to draw the higher or the further Bragg's planes. So this shows first five or six, how many? One, two, three, four, five, six, first six Brilliant zones for a 2D square lattice. And the design looks really beautiful, right? So that's what is first, second, third, fourth, fifth, or higher order Brilliant zones. Is this clear or any question? So now you should be in a position to draw Brilliant zones. Do all Brilliant zones have same size? Yes, very good question, but yes, they have same size. They have equal area. So let me come here. If you try to see, this is first Brilliant zone. If you fold these triangles inward, so if let us try to imagine this as a piece of the paper. So if I and cut it like this, if I fold this triangle, this will be coming to this part, this will be coming to this part, this will be coming to this part. Yes. Similarly, all other Brilliant zones can be folded back to the first Brilliant zone. That is called Brilliant zone folding. So Brilliant zone folding I will discuss in a separate lecture. This is a very interesting lecture in itself. So maybe in coming classes, or I will try to spare one full lecture for that. Yes, that is fine. Very good question, and very important concept as well. Any other question? Yes. Any other question, or is everything okay? Any response? Is everyone present? Mark your attendance. You have to write down the roll numbers here. Okay, I didn't ask you to mark your attendance. Fine. So just type your roll numbers as well, so that it is recorded that you were present in today's lecture. Now let us discuss one more example to make things more clear. So on this web page, so you can note this address here. So this is a site which you can do yourself as well on your mobile phone. Even I think you need Adobe Flash Player, and then you can see these animations yourself carefully. Now let us try to see this for another example of two-dimensional hexagonal lattice. This is again reciprocal lattice. So if you see 2D real space lattice, if that is hexagonal, the reciprocal lattice for that also comes out to be hexagonal. So how to draw? So this is a two-dimensional hexagonal lattice. How to draw Brilliant zones for this case? Again, let us assume this is the central point, the reference point. Let us connect it to the neighbors. Draw perpendicular bisector. Do it for all the 6 nearest neighbors. So this innermost cell enclosed by all these Bragg's planes or the perpendicular bisectors is called first Brilliant zone for 2D hexagonal lattice. This is quite simple. I hope it should be clear. Then let us try to look for second Brilliant zone. Now, okay. Now you will say, okay, that I didn't draw additional perpendicular bisectors to go to the second Brilliant zone, right? So what all area is there while we are getting or going from first Brilliant zone to second by only crossing single Bragg's plane? So this is the area. Now you will ask why I didn't draw the additional perpendicular bisectors. So this will be clear when I draw those additional perpendicular bisectors. So let me draw for these. This is the perpendicular bisector. These are others. So when I go from first to second, these bisectors are not at all coming in between, right? So that is why we don't need to draw those additional bisectors. So it is not the case that, okay, for while you have to go to the higher Brilliant zone, from a lower Brilliant zone, you have to draw the additional perpendicular bisectors. So that is not the case. Or even you can draw all the perpendicular bisectors at once and then begin highlighting your respective Brillouin zones by noting that, okay, how you will go from first Brillouin zone to higher Brillouin zone, second, and then second to third, and so on. So that drawing of perpendicular bisectors is not a mandatory thing. I mean, that you have to draw one perpendicular bisector, additional set of perpendicular bisectors. So that is not the case. Well, so what all will be the third Brillouin zone? So this yellow area is second Brillouin zone. So what all region is accessible after crossing single Bragg's plane? This region, this full triangle, one Bragg's plane, either you go from this side or from this side, this is accessible. So these triangles are constituting the third Brillouin zone. So let us see. Yes, that is your third Brillouin zone. Now, what all will be in fourth Brillouin zone? We need to draw additional bisectors, I think. So this, all these. So this will be your fourth Brillouin zone for 2D hexagonal lattice. Then for fifth Brillouin zone, we may need additional bisectors like this. So this is a careful exercise. You have to do it carefully. Fifth Brillouin zone, sixth Brillouin zone. Wow, here's that beautiful pattern. Isn't this beautiful? Those who are making rangolis, right? You may try to copy such idea of drawing Brillouin zones. Anyway, so now on screen it looks simple and very what I say, very trivial thing, but you do it yourself. Take a graph paper and then draw all those bisectors carefully with the scale. Try to check all those Bragg plane and then try to draw the various Brillouin zones with the help of various colors. This will make your understanding far more better, and you will be in a better position to technically understand what is a Bragg's plane, how to go from first Brillouin zone to second Brillouin zone, and second to third, and so on. Right? So maybe that is a good homework. Oh, very good, Ankush. Find it beautiful. I also found it beautiful. Fine. So, is there any question from this second or third Brillouin zone, or any question from what we did? Okay, Ankit says, do we need all Brillouin zones, or just first Brillouin zone is enough to describe the properties of a system? It's also a very good question. Yes, first Brillouin zone is sufficient. This also is going to be the part of our course. In coming lectures, we will see all these things in details. Now, since I told you about Brillouin zone folding, right? So I can fold back second Brillouin zone to first Brillouin zone, third also to first Brillouin zone, and so on. So means there is a one-to-one correspondence between all those Brillouin zones, and that one-to-one correspondence can be used to describe the information in higher Brillouin zones only into the first Brillouin zone. So that is what we call the Brillouin zone folding. So we will be talking about that in our next classes. So yes, it's good that you have those questions in your mind, means you are technically or conceptually understanding the things, because otherwise we don't know that what is going to follow in the next lecture, and we do have no interest to what is going to come up. So you should actually be happy, or you should in advance should have questions that, okay, what all is going to come up. So these kind of questions are very relevant and natural. You all should have these kind of questions. So yes, in the coming classes we will be doing that. Fine. Because the time is almost over. So is there any question for today's topic, today's contents, what we did? Is there any further question? Anyway, if there is no question, okay, let me show quickly before I bind up the Brillouin zones in 3D. Those are going to be the Wigner seed cells, right? So in 3D, this is for FCC case. Let me first show for simple cubic. So this is the Brillouin zone, first Brillouin zone for simple cubic case. Simple cubic lattice, if you take, then if you draw the unit cell, the simple cubic, for a simple cubic real space lattice, the reciprocal lattice is also simple cubic. So if you draw the Wigner seed cell for a simple cubic lattice, that is going to be a cube. Try to visualize this. I leave it as homework to you. Similarly, this is a simple. And then if you see FCC, the FCC real space lattice, then the corresponding reciprocal lattice is BCC. That also we will do. Maybe you should have done it in your BSc. If not, I will do it maybe later. So this is how the Wigner seed cell looks for a FCC lattice in the real space. Means you have to write down reciprocal lattice for FCC, which is going to be BCC. Then you have to draw the Wigner seed cell for BCC. I hope this figure I had shown you in the previous slides while I was discussing Brilloiun zones, and I had told you that okay, this is the Brilloiun zone for BCC. Now, since BCC is the reciprocal lattice for FCC, this is going to be the Brilloiun zone for FCC lattice. I hope I'm not confusing you with the wordings. This is going to be the case for BCC, for hexagonal. These are all the Brilloiun zones. Fine. This is for tetragonal case. It looks like cubic, but it is not cubic because in tetragonal A is equal to B, not equal to C. So if C is longer, the B3 here is going to be shorter. If C is shorter, B3 is going to be longer because there is a reciprocal dependence. For some other lattices, it may be complicated. For example, for rhombohedral case, the reciprocal the Brilloiun zone is going to look like this. So these Brilloiun zones are very, very important in condensed matter physics. If you don't understand Brilloiun zone, you can't understand condensed matter physics. So I give you a time till tomorrow. I have tried to make it far more simple to you all. But still, if there are doubts, you go to the website which I told you. You can again note this DOIT. This is the link. You may take a screenshot, or maybe I can paste this in the Google Classroom, the link for this website. So from there you can go to this site. Fine. So you understand the aspects of Brilloiun zones properly, so that we could further go to. We can easily discuss various other concepts in the condensed matter physics. So with this, that's all for today. Let me know if there are any questions or everything is okay, then I can say goodbye and good day to you. Is there any question? What is the maximum number of Brilloiun zones? I leave this question to you. You think, and based upon your common sense, you try to answer this question. Tomorrow I will be asking you for the answer. I leave it to all of you. Fine. Okay, there is no question. If there are no more questions, let me thank you all for being a part of this class. And see you tomorrow, or no, it's not tomorrow, next week with the next contents. But so now you have 3 days work, not 3 days time. So you must draw all those Brilloiun zones yourself, and then I will be uploading one assignment. Okay, you will then be clicking photograph of what you have done with your hand on some graph paper, and then you have to upload that photograph as an assignment. So you have to draw how many. So Harish, you try to take a graph paper and then try to draw maximum possible Brilloiun zones, and then each Brilloiun zone will carry 1 mark for the assignment. So more the Brilloiun zones, more will be the marks in the assignment. That is a great idea. Good. So ideally you can get infinite marks. I don't know. I mean, whether you can draw infinite Brilloiun zones or not, that you try yourself. So that is it for today. Fine. I'll be uploading the assignment on the Google Classroom. Fine. Have a good day. Thank you very much.